So we saw that the slope of the tangent line or the slope of the graph is ultimately a function of x for most functions. Um, and really what that's saying is that the slope depends on the location of the graph because most functions have a different slope at different locations. Well, if we start to really think of the slope as a function of your location, location being x, then what we really start to develop is this idea of what we call a derivative. Derivative essentially is one of the two major operations that build what we call calculus. And so the concept of differentiation is that operation of finding the derivative. So we have a definition of a derivative. So the definition of a derivative says that the derivative of some function f at a location x, we will denote using this, which we're going to call f prime of x. If you notice, there's some similarities to just the basic function notation. I'll talk about that in a second. Is given by this. Well, this should look very similar to what we just did a few seconds ago. And so this was the slope of the tangent line. So we're basically saying that the slope of the tangent line or the slope of the graph, which are both the same, is what we're now going to call the derivative. But we're using this notation. The notation is this f prime of x. That little dash we're calling prime. And so the idea here is more looking at it as a function. This is function notation. Now we have a function f of x, and this function we will take the derivative of it and get this, which is f prime of x. But the idea is that these are related. This is a function, f is the name of that function. This is coming from that function, so we're going to use the same name. But by putting this dash, we're saying that we're taking the derivative. That is the notation for the operation that we're doing. You know, we have this is the notation for operation of addition. That's the notation for operation of multiplication. This is one of the notations for the operation of differentiation. And so we're taking the derivative of f and noting that it is another function. In the last example, f of x was x squared plus 2. The derivative, or the slope of the tangent line, was 2x. This is a function, this is a function. But they're related functions in that this is the slope of this. Well, what is slope? Slope is the measure of change from one point to the next to the next. Well, essentially the idea here is that this function measures the change in this function as we move from point to point. So this new function, which we're calling the derivative, is exactly what we were finding when we found the slope of the graph or the slope of the tangent line for a given function. Notation, prime notation, is just one of a couple of notations we'll go over. But it is the slope of the tangent line or the graph, the slope of the graph of a given function. And the process of finding this derivative we call differentiation. So there are a couple of notations when it comes to derivatives. The first one we've already talked about, which is called prime notation. This is prime notation, and it's read f prime of x. Okay? Instead of f of x, because we have the dash, it's f prime of x, hence prime notation. Then we have Leibniz notation. I'll talk about that in a second. Look at this one right here. This is also prime notation. You know that y and f of x are interchangeable. So I can say f of x equals x squared plus 2, or y equals x squared plus 2. In which case, I'm going to find the derivative. I would say that the derivative is f prime of x equals 2x. But if I started off by using y equals, I'm going to say y prime equals 2x. It's just a matter of how the function was given originally. If it's given in f notation, we use f notation for the prime. If it's given in y notation, then we use y notation for the prime. But we still have the prime there. So these two are both one and the same. Okay, then we have Leibniz notation. This is Leibniz notation. This is also Leibniz notation. So let's look at this. dy over dx. Well, the way we read that is dy dx. We don't use the word over. So if we just look at this, we say dy dx. When we look at this, we say f prime of x. So dy dx. It's really dy over dx, but dy dx. What this stands for is dy is the change in y, or the derivative. Let me get a better derivative of y, and then this represents with respect to x. What Leibniz notation gives us is a little bit more information than prime notation gives us. Prime notation is simple notation. I think it's very easy to look at, it's very easy to understand, it's very easy to write. But when you simplify things, sometimes you have to leave out some information. The Leibniz notation does the same thing that this does, but gives us this information. It tells us what we're taking the derivative of and with what variable we're taking the derivative with respect to. Don't necessarily get a whole lot of that here. What happens is as we move forward with derivatives, we start to get into more complex situations where we might change the variable we take the derivative with respect to. In which case, prime notation starts to have to be phased out, and Leibniz notation comes into play more. So dy dx, which is Leibniz notation, is read the derivative of y with respect to x. This variable is the variable you're taking the derivative of. This is what you're taking the derivative with respect to. And that could change. Let's say we had f notation instead of y notation. Well, I could say let's take the derivative of f with respect to x. And that's exactly what this is. I put the f on the side so whether I write it like this or I write it like this. And I put the f on the side, whether I write f or whether I further write f of x. That on the side is the same thing as it being in the numerator, and it's still read the derivative of f with respect to x. The derivative of f with respect to x. And so this notation and this notation are both Leibniz notations. Okay. Then we have Euler's and Newton's dot notation. At this point, those are seen in other realms of calculus. That's not something we're going to necessarily see right now. We would use Newton dot notation probably more in a physics class. Euler's notation would come in a little bit more in advanced mathematics class. If you end up making it to differential equations at some point, you would see something more like this. It's also known as operator notation. And so we're going to ignore these two for right now. I just put them up there so that you have seen them at some point. But mainly focus on prime and Leibniz notation. We'll do prime for the most part to get started, and eventually we'll start working in Leibniz notation. All right, so let's get rid of all this and start thinking about this question here. So this question here says, find the derivative of f of x equals x cubed plus 2x. And this question isn't really that different than what we were doing prior to talking about derivatives. When we did find the slope of the graph or find the slope of the tangent line, this is the same question because the slope of the graph, the slope of the tangent line, the derivative are all defined using the limit as delta x goes to 0 of f of x plus delta x minus f of x all over delta x, in which case we're now calling this thing the derivative of f prime of x. So this question is really no different. I mean, in this particular question, the little bit of a difference is that we're not doing it at some point, right? That's not part of this. We could additionally throw that on the end, but right now we're just focusing on finding the derivative, finding the function that will give us the slope. And so what do we need to do? Well, we talked about how we need to find this, and we need to find this. Well, this is right here. So now we're just going to find f of x plus delta x. Well, it'll be x plus delta x cubed plus 2 times x plus delta x, because that's what the function tells me to do. Well, if I do x plus delta x cubed, I have to get x cubed plus 3x delta x squared. Oh, my mistake. All right, so where were we? Sorry for slight technical difficulty. So we get f of x plus delta x to be x plus delta x cubed. So if we cube this thing, we're going to get x cubed plus 3x squared delta x plus 3x delta x plus delta x cubed. Oops, sorry, there's a square here too. Plus 2x plus 2 delta x. All right, a lot of people always ask, well, where did you get that from? Well, it's from cubing this. Now when I cube this, much like when I square it, I can't just square this or cube this and cube this. You know, this x plus delta x cubed comes from this a plus b cubed, this binomial cube formula. In which case, if I do that, it's a plus b times a plus b times a plus b, which ends up giving me a cubed plus 3a squared b plus 3ab squared plus 3b cubed. Oh, not 3, sorry, 1b cubed. Which would be something you would have learned in algebra. It's the binomial theorem, also known as Pascal's triangle. There's a pattern to sort of multiplying this out. Again, something that if you're having trouble with and you have no idea what this is, you might want to go back and review Pascal's triangle. Okay. But nonetheless, that's where this came from. A being x, b being delta x. So you see x cubed, x squared, x to the first. Then here you see delta x cubed, delta x squared, delta x to the first, which is exactly what's happening to b. You see a 1, you see a 3, you see a 3, you see a 1, 1, 3, 3, 1. All right. The other option is just sit there and multiply out x plus delta x times x plus delta x times x plus delta x, which will take a long time and really not preferable. Anyway, this will go here. So the derivative will be the limit as delta x goes to 0 of x cubed plus 3x squared delta x plus 3x delta x squared plus delta x cubed plus 2x plus 2 delta x minus f of x, which is x cubed plus 2x, all over delta x. It's a lot. Okay? There's a lot going on here. Every problem we've done has gotten progressively longer. And that's going to continue to happen until we kind of put a stop to that and find some shortcuts here. But let's keep moving through this problem. So this negative is going to distribute it through, similar to what we've seen before. This is going to give you negative x cubed. That'll cancel with this positive x cubed. This will give you a negative 2x. That'll cancel with this positive 2x. So what we have is the limit as delta x goes to 0 of 3x squared delta x plus 3x delta x squared plus delta x cubed minus 2 delta x all over delta x. Notice delta x, delta x, delta x, delta x. Delta x is going to 0. That's a problem. But since these all have a delta x in them, I can factor a delta x out. Be left with 3x squared plus 3x delta x plus delta x squared minus 2 all over delta x. I can cancel these two delta x's. And then what I have is, run out of room, the limit as delta x goes to 0 of 3x squared plus 3x delta x plus delta x squared, squeeze this in here, minus 2. Is it minus 2 or plus 2? It's, where are we at? Oh, my mistake. Look at this. Plus 2 delta x, that's here. Plus, plus, plus. Okay. So delta x is going to 0. I have no problem plugging 0 in for delta x here or here, because they're not in the denominator. Remember, we canceled this out. That was the problem. So what do we end up with? All right, let's squeeze this in here. We have 3x squared, and we have plus 2. The 3x squared doesn't have any delta x's in it, so if delta x goes to 0, this doesn't change at all, stays. 2, same thing. They're both treated almost like constants with respect to delta x. This one goes to 0, this one goes to 0. So this right here is my derivative. The derivative is 3x squared plus 2. And so here's your original function. Here's the derivative of that function. What does this give me? This tells me how this function is changing. This gives me the slope of this function at any given point. This is dependent on x. If I have a point on this function, I can then find the slope at that point using this function. But it's the derivative. It's a function of x, but it's related to this function of x, hence the notation, etc. Now look at all this computation we have. Look at all this computation here. Okay? It is getting longer and longer and longer for each problem. But there's a pattern. If you look at the few problems we've done through slopes of graphs, slopes of tangent lines, and now derivative, they're all the same thing. You've seen the similar things happening. Well, all the examples we've done have been for polynomials. If I change the kind of function we're working with, some of these patterns change up, but each type of function has a very similar pattern to how the derivative develops. So what we will then start to learn is how do we come up with these derivatives in a slightly easier way by recognizing the pattern of what's happening. And so while we now understand what a derivative is, where a derivative came from, the concept of how it relates to slope of the tangent line and slope of the graph, the next step that we will spend the next couple of videos working on is understanding how do we get these answers. How would I get 3x squared plus 2 a little bit quicker, a little bit easier than what we just did by looking at the pattern of this relationship to this function's relationship. Before we start talking about those simpler patterns and getting into that, which will take quite a bit of time, we want to talk a little bit more about the derivative and how it relates to continuity and the concept of the derivative possibly not even existing. And so one thing you got to understand is that the derivative is a limit. The definition of a derivative is a limit. And we've seen that limits sometimes don't exist. So therefore, it's possible that the derivative could not exist. And so we need to look at whether or not a derivative exists or doesn't exist and what might cause that and how that relates somehow to continuity, because we've seen in the past that limits and continuity also have a relationship. And so what we're going to do is we're going to use an alternative definition for the derivative. And this right here is our alternative definition to the derivative. If I want to find the derivative of a function at a particular location C, you could use this alternate definition. Now this alternate definition would come through the same means of what we did before, using slightly different notations, simplifying. But we use this one when we're primarily talking about continuity and whether or not derivatives exist. This is not very simple to work with when we're just asked to find the derivative of a particular function at a particular location necessarily. But we are going to use it here. So we have the limit as x approaches c of f of x minus f of c all over x minus c. And so we see we have some of the same issues. If x is going to c, then this denominator is getting closer to 0 because this is getting closer to c. You'd get c minus c. One problem with using this definition is lots of times what we have to do is use one-sided limits to determine if this limit exists. This is a full limit, two-sided limit. But oftentimes to do a two-sided limit, you have to look at the limit from the left and the limit from the right. And if they're equal, then this limit exists. If not, then this limit doesn't exist. And so we're going to have to do some of that, which is why we don't usually use this one, because that's far more work than we would choose to do for some examples. One thing we need to talk about a little bit also is the idea of a function being differentiable. A function is considered to be differentiable at a particular location if the derivative exists. And then if it exists at one location, maybe it exists at multiple locations across an interval. Well, if we're going to be differentiable on an interval, specifically an open interval, then we have to be differentiable at every point inside that interval, which means the derivative has to exist for everything between a and b. And then we can extend it to being differentiable on a closed interval. Well, we have to make sure the derivative exists everywhere between a and b, but then also has to be differentiable at a and at b. We say it's left differentiable and right differentiable, but the idea is the limit from the left and limit from the right have to equal. None of that is really of any consequence at this exact moment, but definitions that I'm going to throw out at you right now. So the idea really is differentiable at a location means the derivative has to exist. Okay? And if it doesn't exist, then it's not differentiable. Now, one thing to understand is that if a function is not continuous, then it's also not going to be differentiable. What does that mean? Well, think about it. If you have a graph that goes like this, and then has an open circle and goes like this, okay? At this location right here, the function doesn't exist. If the function doesn't exist here, how can I talk about there being a slope right here? I can't talk about there being a slope right there. So if there's no slope right there because the function doesn't exist there, then we say it's not differentiable. So not continuous, not differentiable. But we got to be careful with the way we look at this statement. This is an if-then statement, and it can only be read in this one particular way. If this, then this. And you cannot twist that statement up too much and have it continue to be true. But this is true. If it's not continuous, then it's not differentiable. So don't bother trying to find the derivative at any location on a graph where the graph itself or the function itself doesn't exist. All right. So here we have an example where we're going to start talking about something being continuous but not differentiable. Might seem a little confusing. What I'm going to say is, look at this function. This function is continuous all the time. There's no breaks in this graph. It's all one solid piece. But this point right here, the point of that v, is a point where the function exists, it's continuous, but it's not differentiable. What I'm saying is the slope doesn't exist at that specific point. Now you might think that, how is that possible? Well, there's a reason. And it has to do with the different slopes and how those slopes change as we move through the function. And so what we're going to do is we're going to say, okay, well, let's find the derivative at x equals 2. I'm going to use this alternate definition for derivative. So I'm going to say if I'm trying to find the derivative at 2, I'm going to do the limit as x approaches 2 of f of x minus f of 2 all over x minus 2. That was that alternate definition we just saw. Applying it to this specific example, using 2, c being 2. So if the limit is delta x, as x goes to 2 of absolute value of x minus 2, that's f of x, minus f of 2 is 2 minus 2, all over x minus 2. Well, 2 minus 2 is 0. So what we get is the limit as delta x goes to 2 of the absolute value of x minus 2 over x minus 2. And so doing that limit is not going to be easy. One way we could do that limit is to look at it as the limit as x approaches 2 from the left and the limit as x approaches 2 from the right of absolute value of x minus 2 over x minus 2. Now, if these two answers are the same, then that'll give us the answer for this. If these two answers are different, then we could say that this does not exist. So the question is, which one is it? Well, let's look at these two. So if x is approaching 2 from the left, smaller than 2, I plug that value in here and here. Well, if I just look at the x minus 2 and the x minus 2, these are exactly the same. Well, if you take the same thing over itself, you would expect to get 1. However, they're not the same, in that if I do the left side of 2, this is going to be smaller than 2 minus 2. That's going to be negative. Smaller than 2 minus 2, that's going to be negative. Now, they're the same negative number. However, this has an additional operation of absolute value. So that's going to take this and make this value positive. So I have positive over a negative. So overall, my answer is going to be negative. But aside from that sign, this one being positive, this one being negative, the number component, the value component, would be the same. So if they're the same, it's going to be 1. But overall, I'm going to get negative 1 as an answer. If I look at this one, right side of 2, bigger than 2. This is bigger than 2. This is bigger than 2. Overall, this and this are the same. Bigger than 2 would be, minus 2 would be positive. So this would be positive as well. The absolute value as an additional operation would really not do anything to this positive value. It would stay exactly the same as this. So these are exactly the same with exactly the same sign, and I would get positive 1. Well, look at this. The left side, I get a limit to be negative 1. The right side, I get a limit to be positive 1. In order for this limit to exist, which is the full limit, these have to be the same. They're not. So the limit does not exist. But that was the derivative. So the derivative does not exist there, which is what I said earlier. Now I just showed you that it doesn't exist. Why? Well, the reason why is this sharp point. If I was to find the slope of this component of the graph, this is a line and the slope is negative 1. If I was to find the slope of any part of this graph being a line, it's going to be the same all the time, and that slope is positive 1. This specific point, I jump from a slope of negative 1 straight to a slope of positive 1. I don't gradually go from negative 1 to positive 1. I jump from negative 1 to positive 1. I mean, if you think about it, here's negative 1, here's positive 1, 0 is in between. I don't gradually move from here to here. I jump from here to here. And I miss all these in between. Well, that point is exactly where that happens. So I have, this jump in slopes, which causes the slope right here to not exist. And so anytime you have a graph that's going along and then has a sharp point, the slope right there, or the derivative right there, won't exist. Now, if your graph just turns and has a sharper turn, say this is a sharper turn, then that's a sharper turn, what's going to happen is, whether the slope is going from negative 1 to positive 1 faster or slower, it's still happening gradually, and you're gaining all the slopes in between. If I look at the slope here, let's say the slope here is 1, let's say the slope over here is negative 1, and I'm going along this curve, I'm still going to get slopes to be, say, I don't know, a half, then a slope to be a quarter. Eventually I'll get a slope to be 0, and then I'll go slope to be negative a half, and then negative a quarter. I'll gradually, or negative a quarter, sorry, negative a half. I'll gradually go from a slope of 1 to negative 1. But here I'm jumping from a slope of negative 1 to 1, and that causes the derivative right there to not exist. So here's a function that was continuous, but not differentiable. Okay, so here you see another function that's going to be continuous but not differentiable at a specific point. Look at this point right here. This point right here is a place where the function exists, the function is continuous, but the derivative is not. It's not going to be differentiable. Now, for a totally different reason. There's no sharp points in this graph, but the graph does something different, in that if I look at this graph as I move this way, and I look at the slope here, 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 this graph is going up from left to right, which means the slope should be positive. But as I move from left to right, the slope's getting bigger and bigger and bigger. Why? Because the graph's getting steeper and steeper and steeper. So if I looked at the tangent line here versus the tangent line here versus the tangent line here, those tangent lines are getting closer and closer to a vertical tangent line. Now what happens is right here, my tangent line goes completely vertical. And then once I start moving a little bit past that point, my tangent line starts evening off. My slope gets less steep, so the slope is decreasing. It's getting smaller. It's still positive, but it's getting smaller. Well, right at that point, my tangent line went vertical. You should know that when you were in algebra, anything with a vertical line had a slope that we called undefined. Well, what's happening really is it's not that the slope is undefined. It's that the slope was getting bigger and bigger and bigger. And if we took the limit as, say, x minus c of f of x minus f of c all over x minus c, which is our definition for our derivative at c, if we did this limit, what we're going to find out is that this is going to give us the derivative, which is going to give us the slope. Well, that's going to get bigger and bigger and bigger. Well, by the time we get to this location, this limit ends up giving us infinity. We saw that when we get a limit to equal infinity, that technically means that the limit doesn't exist. But this gives us more information. What this tells us is that why it doesn't exist. It doesn't exist because the derivative, or the slope, got so big it went to infinity. So rather than say the slope is undefined, we could say the slope is infinite. Which would be, instead of saying this limit doesn't exist, we can get a little bit more information and say, well, why is it undefined? Why does it not exist? It doesn't exist because the derivative got so big, the slope got so big that it went to infinity. Just for that split second. And the second we move past that point and we go a little bit further on, then the slope starts to come down a bit, right? So we could do the computation for how you see that the limit equals infinity, but that's not the point here, right? Now, right now, the point is essentially talking about we get this infinite value. So anytime your graph gets to the point where your graph goes vertical for a split second at a particular point, you know, here again, tangent line, tangent line, tangent line, tangent line, then it comes back down again. That could cause your derivative to not exist, your slope to not exist. And it's not so much that it doesn't exist, it's just that it went infinite. The slope went infinite. And so another one, continuous but not differentiable. So there's two instances there where your function existed, the function was continuous, but the derivative did not. Sharp point, and when your function goes infinite for a second. So what's the relationship between differentiability and continuity? Well, here's another if-then statement. If f, whoops, let's use a different color. If f is differentiable, then it must be continuous. But be careful how you read that. It's an if-then statement. If it's differentiable, then it's continuous. You cannot say that if it's continuous, then it's differentiable. You can't read this the opposite way. We saw there were two examples where it was continuous but not differentiable. So if you're trying to figure out if something's continuous, we can use differentiability to help us. If it's differentiable, then it's continuous. But if it's not differentiable, you cannot say it's not continuous. So continuity does not imply differentiability. However, differentiability does imply continuity. If you have differentiability, you can say it's continuous. If you don't have differentiability, you cannot say it's not continuous. So that's a very close relationship between differentiability and continuity. However, it's a very, very specific relationship, and you got to be careful with how you deal with it.